Hello. Good morning, Gautam sir.
Sir, good morning. How are you, sir?
Fine, sir. Fine. Thank you, sir. So after 2-3 minutes, that will start, sir.
Sure, sure. We will wait for
Yes, sir.
other 2 to 3 minutes.
Hello. Good morning to all the participants. So I welcome you all in the second day of the FDP on the machine learning. So now this is the second session. Now Dr. Gautam sir is with us. Now let me introduce first. Dr. Gautam has earned his PhD from NIT Rourkela and currently working as an assistant professor at National Institute of Technology, Delhi. Before that, he has served Sardar Vallabhbhai National Institute of Technology, Surat, and Institute of Technical Education and Research, Shiksha Anusandhan University, Bhubaneswar. His area of research includes biometric security, image processing and computer vision, machine learning and deep learning. Dr. Kumar is a professional member of IEEE Society. He is also serving as a reviewer of many SCI journals, including Multimedia Tool and Application, IEEE IT Professionals, Internet Operating and Network Reputation recently at NIT's HM Regional Computing and Robotics and Research Scholar works on various computer vision in which it will be based on the standardized. Now I hand over the session to Dr. Gautam sir. Now please, Dr. Gautam, now take care.
Thank you, sir.
Yes.
Thank you, sir. Thank you so much. So I would like to also thank you, the coordinator of this event, for sharing, for giving the opportunity to share my knowledge with you people. So, sir, can I turn off my video to save the bandwidth?
Yes, sir. Yes, sir. It's up to you. Okay.
Okay, okay. So let me first share the screen. So yes, I hope my screen is visible to all of you. So
Yes,
in
sir.
today's 45 to 1 hour of lecture, what we will discuss, we will focus on the concept of generalization and regularization in deep learning. So again, this is one of the most important part in the deep learning, where the most interview questions have been asked. Means and whenever if you have trained any deep learning model, you must have faced the issue of something like, yes, model is trained accurately and well trained, but however, when we test the uh, performance of the model, it may not produce the accuracy or the performance as we expect, right? So what might be the reason behind this? So these kind of questions can be solved or answered by the understanding the concept of the generalization. So before going to the topic generalization, first I will discuss one small concept that is required for this for understanding the process of generalization, that is called the loss function. Many of you may be heard about this, or many of you must have be aware of the concept of knowledge of the loss function in deep learning. Anyway, I will start from that basic level, so that if anyone can forgot or can brush up the revise the things like. So in these 5 points, what I have mentioned, this like what we are going to cover in this 1 hour session. Like the very first is the understanding of the generalization. Second one is the overfitting and underfitting. This is the issue or challenge, and we when we develop the deep learning model or train the deep learning model, we face this issue almost around every researchers who train the model faces the issue of overfitting and underfitting, and we will see how regularization can be used to overcome such issues. We will also see some visualization methods, means by looking at the learning curve, how we can find, means which is it overfit or underfit or well fit. So coming to the next slide. So if someone asks, what do you mean by generalization? So from the word generalization, uh, there is a sub word, you can say, like the prefix of the word is a general. Like general means like it should be for every kind of data. The same result of performance should be uh, produced by the model with every kind of data. When we say every kind of data means like suppose we have trained the model with one data set and we test the model with other data point which is not available in the training set. If our model can perform well on those data set, that is called the unseen data set. The unseen means the data is not visible, or the model, when the model was trained, that data was not used during the training. That is called the unseen data. So if our model, deep learning model, can produce the acceptable accuracy on those kind of data, we say that our model is optimal. Optimal means it is well trained and well generalized. It can generalized. So I hope you're getting. Generalization means the ability to train the model on one data and test the model in a new data which is not seen by the model earlier. That is called the unseen data. So the goal of generalization is like yes, we need to learn the concept, not to memorize. Like suppose for example, suppose you are solving a maths problem and you find it difficult to solve, right? Sometime as a kid, what we do, sometime we wrote the problem, means we memorize the problem. Yes, by memorize the problem, sometimes we can solve the problem in exams, right? Now suppose there is a minor changes or twist in the problem. The concept is same, but there is minor changes in the question paper. So in that case, if we memorize and if we wrote the problem, we cannot solve the problem. We have to learn the concept. This is what generalization do. Generalization learn the pattern. It do not memorize it. Hmm. So another example, what I have mentioned there, like suppose the very easy and famous example of in machine learning is like the spam. The training the model for the uh, for the detection of the spam, where the incoming mail, the new mail that arrived in our inbox is a spam or not. So what we do, we train the model with spam and not spam. Once the model is well trained, if the model is well trained, it can accurately identify the new mail, whether this is a spam or not spam. Hmm. So by looking at the curve here, I have shown here, you can see that our goal is to identify this dotted line, the optimum, where I have written optimum. We should stop the training process where we find the optimum. Before optimum, it is underfitting, and after optimum, it is overfitting. We will discuss what is underfitting, overfitting. For now, just look at the meaning of the generalization. Means the point where the training loss getting increased. If you see the this generation loss, the upper curve, after this optimum, the point where this dotted line cross the curve, after that point, generation loss is getting increased. So the point where it start getting increased, we stop the training. Means our model can generalize up to this point. Beyond this, it is overfit, and before this is underfit. Hmm. So if someone asks you like, what do you mean by generalization? In simple word, you can say that it can perform well on training data set, but when we test the model with the data which was not available or which was unseen, model cannot perform well. We can say the model is not generalized. If model can perform well on those data too, in real time data too, then we can say that model is well generalized. So before moving towards the generalization uh, and overfit, underfit, normalization. So let me discuss the concept of the cost function. What do you mean by cost function? Now, suppose mm, I have a few points, like I have a few points where in x-axis I have, for example, suppose age, right? And y-axis it denotes the weight. So there must be for age like 5 years, 10 years, 15 years, 20 years. Now suppose 5 years weight is 15 kg, 10 years weight is 20 kg, 15 years weight is 30 kg, whatever it is, 20 years is 40 kg. So 5 years weight is 15 kg, 10 years weight is 20 kg, 15 years weight is 30 kg, and like 20 kg. So what we can do, we can draw a straight line that passes through this point, right? So here is the two things. First, what we need to find the slope. Slope. What is the slope of this line, and how this line can be presented? Of course, this is the straight line, and any straight line can be presented with the equation y equal to mx plus c, where m is the slope and c is the intercept. What is intercept? Intercept is the suppose if the line passes through the origin, then intercept c is 0. If the line passes through 1 and this is 2, this is 1, this is 2. If the line passes and the through the some like the y-axis here 1, so we can say the intercept is 1. This is the mathematics, the 10th class mathematics. We all are aware of this, right? So what we need to focus on the intercept. What is the intercept and what is the slope? What is slope? Slope is the changes in y-axis for unit change in the x-axis. Like suppose if we drop the line below this line and this line, so this is the change in the x-axis. Like let's say delta x. For a small change in the x-axis, how many change in the y-axis we got? This is called the slope. This is called this is the basic definition of slope. For every unit change in the x-axis, how much changes in the y-axis we have. Right? So now in machine learning or deep learning, you will see sometimes somewhere we present the equation of the straight line something like this, the well-known equation of the straight line. And also you can see like somewhere y equals to theta 0 plus theta 1x, where theta 0 is the nothing but the intercept and theta 1 is nothing but the slope. See, x is the coefficient, theta 1, x is associated with theta 1, and here m is associated with x. That means m is similar to the theta 1. So theta 1 is the slope and theta 0 is the intercept. This is the alternate representation of the straight line, right? We can also represent this sequence line like in most books. You can see like j of theta equals to theta 0 plus theta 1 x. Not j of theta, or sometimes hypothesis. If you say the hypothesis h of theta x, h is means hypothesis, right? So this is nothing but all three are same. Equation 1, equation 2, and equation 3. All three represent the equation of the straight line. But the difference is that the how we represent. So in machine learning or deep learning, we generally do not follow this notation in many books. We put the intercept and slope in terms of theta 0 and theta 1. So I will be covering this kind of notation, which is also uh, taken by the Andrew Ng. You must be aware of the Andrew Ng. He also used the same notation. So yes, now we know what is the intercept, what is the slope, right? So how the cost function can be designed? The equation of the cost function can be designed using these two concepts. Let me draw one example again. Now suppose I have this is x-axis and this is y-axis, whatever it is. So suppose I have some points, like some points here, some points here, some points here, some points here, some points here. So my goal is to draw the straight line which accurately, which can best classify these two, this data set. And we have n equals to 5 where there are 5 points. We have 5 points in data set, small data set, 5 points. So our aim is to draw the straight line which can accurately classify these data sets. So suppose this is the best equation. This is the best straight line I have found. This may not be best. We can change the value of intercept. We can change the value of slope. We will get the numerous straight line. So suppose for this line, what we have intercept for this particular straight line, we have intercept theta 0 equals to 0 because this passes through origin. And suppose theta 1 is the slope, right? If I change the intercept value, if I change the theta 1 value, we will get the numerous straight line. And we need to find the straight line which can best classify this data set in two classes, right? But there is a problem. These are my actual data point. These are my actual data point, right? When we train the deep learning model or machine learning model, it fits a straight line. This is the straight line. It fits a theta 0 plus theta 1x. Suppose this is the equation of the straight line, right? So what we do again, we find the projection. We find the projection of this straight line on this predicted line. So like this is here, this is here, projection of this point, projection of this point, projection of this point, right? So these are our real point. Real point means actual data point, data set, real data set point, data set point, right? And these are the outcomes of the predicted point, predicted point, predicted point, right? Now can you guess, is there any error between uh, real point and dataset point? Yes. See, this is the actual data point, real point, and this is the predicted point, and the error is this part. This part is the error. Here, see, here error is more. Like if you see this first data point and this predicted point, here see this part is the error. This part is the error. This distance is the error. So here error is less comparatively to this data point. Again, this is the error. This is the error. This is the error. Now suppose for this point, the first point, suppose HF theta x is the predicted point and y is the actual point. So what is the difference? The difference will give the error part. Getting a point. This is the actual point, which is represented by y, and this is the predicted point in the straight line. This is denoted by this h of theta of x, right? And the difference between these 2 points, or these two distance between these 2 points, is called the error, right? But this distance is only for 1 point. Now we have how many points? We have total 5 points, right? In our data set, I have total 5 points, n equals to 5. So what we'll have to do? We have to do the summation of I equals to 1 to n, where n equals to 5, right? Means we need to find the sum of all distance. Sum of all distance, this distance, this distance, this distance. Suppose this is d1, this distance is d2, this distance is d3, this distance is d4, this distance is d5. So what this equation will do? This equation will do some very uh, easy difference d3, d4, d5. The same thing this equation is doing, but I have written it mathematically in a general term, like yes, h of theta. So okay. So what I will do? Yes, I will write here I, since we have 5 points now. So for 5 points, we will perform this kind of operation. So actually, this is adding this equation, this representation, or this summation is adding the the sum of the all distance. That is also called the error. So, but this is not the cost function, because cost function actually it represents the average of this value. So what this equation is doing, this equation simply adding the all errors, right? But there are two things. The distance may be negative, right? This distance may be negative also. To avoid negative distance, what we do? We do square, right? So if we even if the difference between these 2 points is negative, the square will make it positive, right? Also, this is also called the sum of the square error, right? And what we do to find the average, we do 1 by n, right? To find the average, we do 1 by n. So they are n points. Now, in some books, you may find instead of n, they write m number of points in general. So they will divide 1 by m. That depends on the how you do. We also divide each by 1 by 2. Why 2? We also divide each 1 by 2 because when we perform the differentiation of this value, this makes the calculation easier. Like if you like, what is the differentiation of n? If you differentiate n with respect to x, you will get n raised to the power x by n minus 1, isn't it? So if now suppose you have value x square, if you differentiate this value with respect to x, what you will get? 2 will come here, twice x, right? And if we differentiate x square by 2, x square by 2, so what will we have? 1 by 2 multiplied by twice x. The twice will get cancelled. The result will be the x. So to make the differentiation easy, we divide it 1 by 2, and it won't affect the performance, the error value. Dividing by the two constant term, it won't affect this value. So what we can write the final equation. The final cost function can be written as j equals to theta 0, theta 1 divided equal to 1 upon twice m, right? Twice m or n, m is the number of data points, or n is the whatever you write. I equals to 1 to m, right? And what is it does? This is the predicted point, right? Minus this is the actual point, difference of that, and multiply by square. So this is called the cost function of the model, deep learning model. This equation is very important because whatever you will do, we have to come across through this equation. And sometimes in the interview, if you're PhD student, sometimes in the interview, uh, they may ask you to derive this equation, means how you can interpret this equation. So basically, simply you need to draw this the diagram that we have drawn here. You can draw the diagram this using this x and y axis to the diagram. You can show them the distance between the actual point and the predicted point, and the difference between those two distances calculated by this summation. This summation will actually calculate the distance of the actual point, y is the actual point, and h of theta xi is the predicted point. Sometimes in some book, we represent it using y hat to make the things easy to represent or understand. Sometimes we present this in y hat. Y hat means the predicted point and y means the actual point. The same thing. We find why we do a square to avoid the negative value. Why we do the summation to find the sum of the all points wherever there is an error. And why we divide by m, because to find the average 1 by 2 make the calculation easy, because there is a square term like, and this is same thing, right? So this is the cost function. Let me write here the cost function of the model. Now so we won't go, so only this much concept is required to understand the overfitting underfit. So additionally, by changing the value of theta, by just to introduce you, by changing the value of theta 0.50, you can plot a curve something like this is your suppose this is your theta 1 and this is your j of theta, means the cost function, like, right? So this is a 1, this is 2, this is 3. So definitely there will be 0.5, this will be 1.5, and this will be 2.5, something like. Similarly 1, 2, 3. So by changing, when you put theta value equals to 1 and you calculate the j of theta, so you will get the value which is here. You can do it by yourself at your home. So if you change the value of theta 1 to 0.5, you will get for theta 1, for this you will get a value of j of theta equal to 0. For 0.5, if you change, you will get value of something 0.58. And when you put theta 1 equal to 0, you will get value something for 2.2 around. So if you plot this curve of theta 1 against j of theta, so you will get something equation curve something like this, okay. So you will get curve something like this. Let me draw the curve again. So you will get a curve something like this. So this was the positive slope. Theta 1 is nothing but the slope. For negative slope, you will get symmetry of this. This curve is found due to the positive slope, and value of theta 1 equals to 1.50. Similarly, at a different value of theta 1, for negative slope, you will get this curve. And this is nothing but the gradient descent curve. You must be aware of that, the gradient descent curve. And our goal is to reach this value. This is called the global minima. Global minima. So in any deep learning model, when we train, our objective is to find the global minima. Global minima means where j of theta means error. J of theta means error. If j of theta equals to 0, that means called the model is 100% accurate. But in practical, it is not possible to have the error value 0 in practical. Till now, what we do, we always optimize the result. We try to optimize. We train the new novel deep learning frameworks just to optimize the result, or conversely, to improve the accuracy. So what we do, we always try to optimize the value to reach the global minima, right? Anyway, so for our discussion, this cost function is required. This equation is required for our discussion. This equation is required. So you just look at this equation carefully, right? Okay. So here in this slide, uh, I have presented a figure which actually shows the underfit overfit. Now, let me first discuss the overfitting. Before going to this, first let me first discuss the overfitting. Overfit with example like overfitting. Over- Overfitting, right? Now, suppose again in my model, in my training model, I have only two data point. In my training model, I have only two data points. So we are training that model with only two data points. For example, suppose. So this might be the into the straight line. Now suppose you trained the model with two data points and you found the best straight line, best fit straight line. So what is my actual point here? Actual point is the cross point here, right? Cross point here is the cross point is my actual point. Now, if someone will ask you what is the actual point, this is, let's denote it with y. Actual point is always not always, but the general way of printing is y. And what is the predicted point? Predicted means y hat, or sometimes what we say we write h of theta x. Both are same. This is the only way to represent. So why is y hat? Y hat is the point where actually it falls on the straight line. So I am circling it, right? So from this observation, what we can notice? We can notice that yes, the actual point and the predicted point is same. Means the distance between the actual point and the predicted point is zero, isn't it? Now, if I write the cost function here, 1 upon twice m summation x I equals to 1 to m h of theta xi minus y. So what you will get? This point and this point, both points represent the same value. So this will make it 0. This will make it 0, right? Therefore, what is the error function? Error function we got, there is 0. Error means 0. Means the model is well trained. The error or loss value or the cost function value is 0. That means model is 100% accurate. What does this mean? This means when we are training the model, we got 100% accuracy. So you will, if you have trained any model, you will get something curved like something this. This is the training curve, and this will touch the one here. So model is 100% trained. So I think if you have done any model training using any data set, so you must have, normally what happens, it actually do not reach the 100%, it reaches 99.9 or 99.5 something somewhere. There is a small gap between these two, between 100%. If you achieve the 100% training accuracy, that's you should doubt. The 100% training accuracy means the error is 0. Error is 0 means your all training point, the best line passes through this, your training point. That means your model is overfitting somewhere. Now, for now, suppose in future, suppose you got this data point, right? This data point, and this is the actual data point, the real-time data point. So if you project this actual data point on this straight line, what you will find, this is your predicted point. This is your y hat, this is your y hat, and this is your y. And there is a large difference between y and y hat. The error is more. That means your training accuracy is 100%. Why 100%? Because the loss is 0. But when you tested the model, it fails to give the acceptable result. This situation is called overfitting, and let me show you with this example. See overfitting, how the line is getting overfitted. It actually accurately classify every sample. This is called the overfitting. So the similar situation is here also. That's why I have discussed the cost function or error function or loss function first to make you understand how actually overfitting, how deep learning interpret when we write the code by importing the library functions from the scikit-learn. It is easy. We do not know what is going on inside, but this is the mathematics behind the overfitting. So when you train the model, the best fit line actually passes through the points of the data set you have or you are training with. So that's why we are getting the accuracy 100% training. And when we train this new model, a new data point or new data, so it fails to produce the accuracy. So once you train the model, if you are getting 100% training accuracy, you should once look into this whether this model is overfitting or not. And what is underfit? Underfit means like see here, model is not well trained. Model is not well trained. It is still in training process. I mean, it still needs the training. And balance means that is called the well fit. Means it is neither overfit or nor underfit. That is called the best fit. The same thing here. Before the left side is see that loss is still decreasing. That means that it's underfit. And the point after which the loss is getting increased, it is called the overfit, and the point at which it is balanced, that is called the well fit. So while training deep model, our aim is to find the well fit, so to stop the training process at well fit. And there is one more concept that is actually asked in the interview question. Even I was being asked with this like the bias and variance. High variance means the overfit, and high bias means the underfit. So this thing, uh, I think we must have be aware of that. Like anywhere it can be asked, whether it is the MNC companies or you go for interviews in any academic institution or research activity. So this kind of overfitting occurs when there is a variance is high. What is variance? What is bias? Let me show you with this example. Now see here. We will compare these two. Uh, we will compare these two, and this one, and this one, and this one. We'll compare this one. This one. See, see here. See, variance is high, right? See the green curve. Variance is high and bias is low. Right side. Variance is high and bias is low. Now compare this fourth quadrant where the variance is high. Yes, variance is high and bias is low. So this is called the overfit. Actually, this is overfit. This side is overfit, right? Now see this curve. Here the bias is high. Here in left side, the bias is high, right? See the bias value is high. From here, this decreasing. Bias is high, and variance. What is variance? Variance is low. And now see the where bias is high bias, and low variance. Low variance, and high bias. So this is the underfit, and the well fit means low bias and low variance produces the optimal fit. So whenever you face similar kind of question, you can picturize this curve. Whenever you find similar question in an interview or anywhere somewhere, so you can picturize this two images to remember that, like, yes, if the variance is high, if the variance is high, if the variance is high variance, and bias is low. So what variance is high, and bias is low, we got overfit, right? If the variance is low and bias is high, we got the underfit. So when we get well fit, we get well fit when there is low bias and there is low variance. This is a quadrant. You can understand this is a quadrant. This you can as a quadrant, right? So if low variance and low bias, low variance and low bias produce the optimal fit. So this is the situation where we got the optimal fit. Now, from these 3 to 4 slides we have discussed, I think few concepts are clear. Means how the cost function is represented, right? Hmm. What is overfit, what is underfit, and the relation of overfit and underfit with respect to bias and variance. These 2 to 3 concepts I think we have discussed right now. Hmm. Right. So again, one more representation here. So while training the deep learning model, you must be you must have drawn the learning curve from the history of the model history. You can draw the learning curve. So just by looking at the learning curve, you can you can you can analyze where your model is overfit, underfit, or well fit. So see here, this is under training now, this is under training, and this error is still we are getting decreasing. After every step error is getting decreased. So if you draw the curve for this point, this is the underfit, means model is not trained yet, model is still need training. So what we do, we train the model with more epoch. Now suppose, for example, I can write like here 0 epoch, here 20 epoch, here 50 epoch, here 80 epoch, and this is suppose this is 100 epoch, right? Epochs. At 50 epochs, what we found that yes, after 50 epochs, the prediction error is getting increased. See here, prediction error is getting increased. That means this is the point. This is the point. There is a 50 epochs. After 50 epochs, you are getting your error is getting increased. That means now your model is overfitting. You should stop training there. You should stop training at the epoch of 50, because beyond 50, your error is getting increased. See here, your error is getting increased and your model is getting overfit. So this is called the best fit. Best fit. This is underfit. UF means underfit. And if you draw the curve at the epoch of 80, so what you will do, this is overfit. See, this is how overfit is represented. It connects every data point. It connects every data point. This is overfit. So that's why sometimes when we draft a paper or we submit the paper, sometimes reviewer ask to include the learning curve. So just by looking at the learning curve, a reviewer can analyze whether the experiment you have performed, the model you have trained is well fit or underfit or overfit. So if you don't represent this curve, so in that case, it might be a bit difficult by looking at the result, but the visual presentation of this learning curve is like that. So our aim is to find this error, something like this. So the ideal curve should be like this, right? The ideal curve should be like this. So it should decrease and after a certain point, 100 epoch, for example, it converges. It will never meet. There will be gap. So this is your training error and this is your test error. And test error should be less than the training error. This is the ideal situation. This is what we expect when we train the deep model, right? So I think now onwards you can also train the model, and by looking at the learning curve, you can estimate whether this is underfit or overfit, right? So why overfit? There are multiple reasons like the model capacity. If you increase the number of parameter or the depth of the layers in deep learning sequential layers. So due to the high number of parameters, sometimes it start the memorizing the data instead of the learning the pattern. Converse to this, if you have the small data set where the number of samples are not enough, very small data set. So in those situations also it cannot generalize like uh, the use of L1 L2 ridge and lasso. You must have heard about ridge and lasso. So we use this in the deep learning. If you have a trained deep learning model, you must have written the code. In that layer, you can see the L1 and L2 they use kind of this. Too many training epochs again, unnecessary training the model. Even the model has been converged. The training loss or training error is not going to increase or decrease. Still, you are training the model. Sometimes it may cause the overfit and noisy data. Obviously, noisy an irrelevant feature. What happens when we produce the irrelevant feature in the features in the data set? Model starts learning from these irrelevant features instead of important feature. Along with the important feature, it also learned the pattern from the irrelevant feature. This might be the reason of the overfit. There are multiple reasons. Now the question is, yes, overfit might be there, overfit, underfit might be there. So how to overcome these situations? So there are a few famous methods which we as a deep learning developer or researcher we used is the data augmentation. So if you have less data or less number of samples in your data set, you can generate data augmentation. I will show you in the next slide. The use of regularization, dropout and NLP, I will show you. Early stopping is the concept where we do not need to train the uh, deep learning model multiple times to find the best line. We train the model using the early stop, and the model automatically stop the training when the desired accuracy is achieved. And sometimes just by reducing the number of layers, reducing or deleting the number of layers, we can overcome the situation of uh, overfitting. Okay, anyway, and these are the other methods. It's like so if you have a less number of samples in your data set, so what we can do, we can use the cross validation concept. Like you must be aware of this k-fold cross validation, right? K-fold cross validation, where what we do, we divide into, suppose k equal to 5, we divide the data set into five splits. See here, 5 split. We train the model with 4 split or 4 sets. We test the model with fold 1, right? So in next iteration, what we do, we train the model with fold 1, fold 3, fold 4, and fold 5. This is set, and we test the model with another, the one we left while training. Similarly, fold 1, fold 2, fold 3, fold 4, and fold 5. We keep it separate while training in all 5 iterations, and we train the model with remaining folds. Sometimes this overcome the situation of the overfit, and this is usually used to when we have less number of samples in our data set. So one more variant of k-fold is stratified k-fold. Stratified k-fold. They work similar to the k-fold, but the difference is that they find the ratio within a set. They find the ratio within a set, right? Now suppose in one set you have 10 images. Suppose you are training with image. In one set you have 4 images. In another we have 10 images. So if you are using 80% image to train the model, so out of 10, 8 image will be used to train because the 80% you have taken, and with 2 images you will be tested. Now for 4 images, the 80% of 4 is 3.2. Yani 3 images will be trained and 1 image will be taken to test. Again, now suppose there are 20 images in one fold. In one fold you have, this is fold 1, this is fold 2, this is fold 3. In fold 3 we have 20 images. 80% of 80% of this 20 will be taken to train the model and remaining will be tested. Means it will take consider the ratio within a fault. This is also like gives better performance even compared to the k-fold when we have imbalanced data set, or they are like leave one out of cross validation, or this smart is also there. So these are the various techniques that is used to overcome the situation of the overfitting, especially when there is a overfitting. So now come to the how regularization can be used to overcome the situation of this overfitting. Let me first tell you what it does. First, the ridge that's also called L2 regularization is also called L2 regulation. So what actually this ridge regulation do? It actually uh, penalize the loss function. Like see, if you remember, when the model is overfit, what it produce y dash minus y equal to 0. Means there is no loss. So whatever your actual data point, what is your predicted data points, the difference between actual, this is your actual and this is your predicted, difference between these two data points is 0. That means what? That means the loss function j of theta is 0. The loss is 0 means accuracy is 100%, right? So it actually penalizes the loss function by adding a small term that is called, let me write this, y hat is your actual, sorry, predicted, and y is your actual. It add one small term, let me mark it with other color. It add a small term that is called lambda slope square. Earlier it was 0, now 0 plus some small value. That means earlier your j of theta means error. Earlier it was 0. Now L2 regulation penalize this loss function by adding this term. This term is important. Adding this term. Now what is lambda? Lambda is the hyperparameter that is usually set to 1. By default in Keras, the value is defined to lambda equals to 1. Otherwise you can change, but we the hyperparameter, these are the hyperparameter you can change while training, but normally it's set to 1. Now what is slope is like theta 1 we write. Now suppose for a given line, for the condition where we seen here previous, the overfit condition, where the difference between actual and predicted point is 0. Now due to L2, now suppose the lambda value is 1, now slope is 2. So you will get the total error 4. Now my aim is, we got the total error 4. We got the error something here 4, right? Now my aim is to minimize this value 4 to reach the optimal value, right? So what we do? We will change the slope. Now suppose you change the slope. Now, earlier theta 1 equals to 2. Now suppose you change the slope. Now you have theta 1 equals to 1.5. So what your equation will be? 0 means the difference between the actual and the predicted point plus lambda value 1. Now this is 1.5. So you will get something value like here you will get very close to 3. So now we have reduced error from 4 to 3. We have reached 3. Now still my error is not minimized. We need to reach the global minima, right? So similarly, what we do, we change the value of theta 1 from 2 to 1.5, 1.5 to 1.5. We change the value of this theta 1 slope. We change the value of slope. Suppose this is earlier slope, now slope, now slope. We change the value of slope and we stop where we get the minimum value. This is how the this L2 regulation works, right? Now we have another regulation that is called the L1. Now see, L1 is also called the last row. L1 is also called the last row. So in interview, sometimes they ask, what is difference between L1 and L2? What is difference between L1 and L2? Everything is same except one thing. Like earlier in L2, what we did, this is the predicted value, this is the actual value, and we find the square of this, right? So here also we use the term lambda. Here also we use the term lambda, but instead of squaring the slope, what we do not square. We find the modulus of the slope. So this is the difference. This is the difference. Earlier, what we were doing, we were penalize the loss function by adding the term lambda multiplied by slope square in L2. And what in L1? In L1, we do not square the slope. We take the modulus. We take the modulus. A modulus means what? Modulus means, now suppose h of theta x equal to theta 0 plus theta 1 x plus theta 2 x x2 x1, or suppose theta n xn, right? So what is, see, modulo x is not our, x is the coefficient, x2 is the coefficient, xn is the coefficient. What is the slope? Slope is theta 0, theta 1, theta 2 up to theta n. This is the slope, and we find the modulus of the slope only, right? Now what is the benefit of L1? So L1 has, this is the most famous interview question. L1 has two benefits. One, it prevent overfit, and another one is it can be used as a feature selection, or 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 we can say it remove less important feature. This is the most important question in the the in this particular concept, the in regularization. What is the difference between L1 and L2, and how L1 can be used to for feature selection? So what could be the logic? The logic could be any small value. If you take the modulus of the small value, small magnitude, or a small slope, it will get neglected or ignored. So small, the feature which is has less important will have the less slope, and that will not be considered while training the model. So this is the reason why only the highly important feature will be used to train the model. That's the reason it is used for feature selection and prevent overfitting. So the same thing I have written here. Another one is now 5 minutes more. We will complete the discussion. So another concept is dropout. Dropout means, like, what we do, we set the few neurons to the value, something what we say is dead neurons. Like, yes, we just drop out the connection. Now suppose if you want to make this neuron dead, so just cut all connection with this neuron. See here, now this neuron is not associated with any other neurons. Like, yes, Similarly, for this neuron, this neuron, this neuron, this neuron, this neuron, these 2, 3 to 5 plus 1, 6 neurons are not connected with any other neuron. That is called there is actually the concept of dropout. Now, how to find which neuron we should avoid any connection? Actually, in deep learning, we have code something like this. Now, if you write the 0.5, matlab, that means 50% neurons will be disconnected. If you write 0.1 means 10% of neurons, whatever number of neurons you defined in your layer, 10% neuron will be deactivated, means there will be no connection. This is the concept of dropout. Now data augmentation. Data augmentation actually, if you can see here, data augmentation, there is a function in scikit-learn, image data generator, right? So here we have what kind of augmentation you want. Here rotation range equal to 45 means the image will be rotated by angle of 45 degree. Again, shift in width or shift in the height, shear in 0.1. Zoom range means 5%, right? So yes, here is a vertical flip and horizontal flip. So this kind of augmentation you can perform to increase the data set size. Let's see here, the output will be something like this. This is the original image. You have applied the transformation, vertical flip. This is the vertical flip. This is the rotation. This is the blur. This is the grayscale, contrast, exposure. So that depends on how many kind of transformation you want in your data set. This is how data augmentation works. Early stopping, the concept, like, yes, here early stopping, what we do as the model finds, so the point where the testing error is getting increased, at that time model stops the training process. That is called the early stopping. From the name itself, early stopping, how it can be implemented. Again, in Keras we have the keyword patience equal to 3. That means what? That means in the last 3 epoch, it will check whether the testing error is decreasing or not. If in the last 3 epochs, the testing error is not getting decreased, then model will stop the training process, right? So you can change here. You can put 3 or last 10 epoch, or you can last 5 epoch. That depend uh, on the developer, right? Right. So yes, batch normalization is one. Uh, this not that much important, and the last thing is the transfer learning. Uh, so now it is now the classical method. Now still people we use to avoid the overfit condition. So instead of training the model from the sketch, what we do, we put few layers common. See here, common layers, and we change only the top few layers, mostly the number of neurons. The entire model is kept freeze. We only modify the output layer as per our requirement. Suppose it was initially designed for binary classification. Now I want multi-class. Multi-class means more than 2 class. So we can modify the upper layer according to our requirement. The remaining layer will be as it is. So this is the concept of transfer. So in this discussion, what actually we did not discuss the entire deep learning. There are many more things, but we only focused on the generalization and regularization. So what we learned here, what we discussed here, like what is the loss function, how the loss function is represented mathematically. Yes, and when we say the overfit, when the predicted point and the actual point is same, So difference will be 0 means the error will be 0. Error will be 0 means the accuracy will be 100%. In that case, we claim that the model is overfit. So what we do to avoid overfitting, we use the regularization L1 and L2, right? L1 is lasso, L2 is the ridge. So what we did, what these two regulation does actually, this actually penalize the loss function by adding a term lambda multiplied by slope square in ridge or L2 and lambda multiplied by slope, modulus of slope in L1. So these are the main things I want to focus in this 1 hour talk. So later, if you can contact me if you have any query, or in future if you want to do some kind of work in collaboration, you can contact with me anytime. So thank you for I'm open for any question.
Hello.
Yes, sir.
Yes, sir. Sir, actually, there are two queries
Mm-hmm.
from the participant. So, are you able to see the chat box?
Yes, sir. Can I stop presenting the screen?
Yes, 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 yes. Sir.
Yes, the first one is why we are doing the augmentation, right? So now suppose, so deep learning is always hungry to increase the training size or to train for a particular type of function like blur. No, actually, to increase the training size, we do the augmentation and training size just by replicating the same image into multiple image do not generalize the model. It will also increase just copy paste. You do one image, we copy one image and paste is 10 times, it will make the 11 image, but it won't generalize the model. So what we do, we apply different kind of transformation, like horizontal flip, vertical flip, rotation, blur, like shear transformation. So actually that type of transformation generalize the model. So basically you can say, if someone will ask you in interview why we do normal data augmentation, you can say like, yes, to increase the training size, and along with that you can also add one point to avoid the overfit or underfit due to the small data size. We do the data augmentation. And one question is, yes, this is the important question, very important question and very interesting question, the use of L1 for feature selection. I think I have discussed this in brief due to the less time. So what we actually do, L1 features, we use the in equation. If you see the mathematical equation, this is the modulus operator, and the property of the modulus operator is the feature which has a less slope, मतलब numerical value, which has less value as a slope, that because of this modulus operator that will be ignored, and the feature, an important feature will have high value, and that only high value will be kept while finalizing the model with L1 regularization. So simple, in simple word, if someone will ask you how L1 can be used as a feature selection, you simply can say that the modulus operator neglect or ignore or remove whatever it is. The L1 function, the L1 regularization remove or ignore the less important feature, because the less important feature have less theta 1, theta 0, what that value, slope value. So this is the you can say, right? So third question is, what are the matrices used for evaluation of transfer learning? Will sometimes transfer learning negatively impact our accuracy? Uh, so this question is like depending on the application, like the data set. Uh, in my experience, I have never seen like the transfer learning actually decrease the accuracy. It always increase, or it will it produce the similar accuracy. But till now the work my students have done and I have been doing, we are not getting the transfer learning is negatively impacted. But sometimes maybe depending on the data set, it may decrease. If the see the transfer learning is that you have trained the model with dataset D1. Now in your work you are using dataset D2, and if D1 and D2 are totally different, in that case it may impact negatively. Suppose the D1 is the image dataset and D2 is the .csv file where the numerical values are there or the time series values are there. In those cases it may affect negatively. Otherwise, if in both cases it was image or it is trained with similar kind of data, in those cases it will either perform the similar performance or better, definitely better. So I think I'm clear. Any other query? I think, sir.
Yes, I think there
There
is
is,
no
there is no more question.
So thank you very much, sir. Thank you for this wonderful lecture.
Thank you, sir. Thank you, students, sir. Thank you, Vikas, sir.
Thank you, sir. Thank you for your time.
Sir. So can we stop, sir? Yeah.
Sure, sir.
Yes.
Sure, sir.
Yes.
Okay. Thank you. I'm leaving. Thank you.
Thank you so much, sir.